Hello, in this video we discuss the paper Hidden Technical Debt in Machine Learning Systems by Scully et al. And published in NIPS 2015. This video is presented by Mihir Kale, Mansi Gupta and myself Radhika Parekh. The video presentation is outlined as followed.
ठीक था फॉलोड का फॉलोज कर देती कुछ नहीं होता.
Hello everyone, in this video we discuss the paper Hidden Technical Debt in Machine Learning Systems by Scully et al. Published in NIPS 2015. This video is presented by Mihir Kale, Mansi Gupta and myself Radhika Parekh. The presentation is outlined as follows. We start with an introduction of the concept of technical debt, followed by the risk factors in production machine learning that could accrue technical debt. We have identified crucial aspects of production ML that the original paper does not cover and discuss those through relevant literature. In traditional software engineering, technical debt is the implied cost of additional rework caused by choosing an easy solution now instead of a better approach that would take longer to develop. As ML applications become increasingly coupled with traditional software systems, the issue of technical debt in software development holds for production ML as well. The paper highlights ML-specific risk factors that could lead to technical debt. The authors also propose design patterns and best practices for scientists and engineers that can mitigate this debt. The first risk factor is abstraction boundary erosion. Complex models can erode traditional abstraction boundaries in the code. Tweaks in the model, such as adding features or tuning hyperparameters, or the existence of hidden feedback loops between model output and input features could have unprecedented consequences. For example, adding a new feature will alter the weights of all the other features. Sometimes the model output could also revamp itself as an input feature to the model, and this could lead to a hidden feedback loop. The authors refer to this as changing anything changes everything. The authors suggest ensemble models to isolate such effects and carefully monitoring the model for feedback loops and anomalies. The second risk factor is data dependencies. They say your model is only as good as your data, and quirky data can often have undesirable effects on model output. Regular re-evaluation and refactoring of the code can mitigate the effects of redundant input features, bundled input features, data dependencies, and dynamic input signals. For example, a retailer changes the product numbering scheme, but this is not incorporated in the sales prediction model, which still uses the old schema. This could potentially be disastrous if the database is purged of the old numbers and the corresponding metadata. The third risk factor is system-level spaghetti. Poor coding practices, experimental code paths in production, unstructured data pipelines, and the overuse of library packages can make debugging and maintenance difficult. This leads to loss of time in terms of man-hours, waste of computing resources, and/or production issues. Holding ML systems to the same stringent coding standards as other software applications with code refactoring, holistic data pipelines, unit tests, and proper configuration files can mitigate these effects. The fourth risk factor is changes in the external world. Changes in the external world may affect both model input and output, accruing debt in terms of model design and expensive feature engineering. Assumptions about feature correlation can fail to hold, while hard-coded action thresholds for model output may not be desirable in the current context. It is essential to re-evaluate input and prediction distributions to recover this debt. While the paper does a good job of bringing technical debt in machine learning to the forefront, it tends to focus more on model-specific issues and not how ML applications can be integrated into mainstream tech processes to reduce technical debt accrued by the same. Also, the potential socio-technical debt of ML in domains such as finance, say by using adversarial environments like convolutional neural networks, is not looked into. This is particularly important in fields like credit rating, where people can game the system. While the original paper touches upon the quirks of data, not much is said about engineering robust data pipelines, how ML applications should be tested, or reducing technical debt using model interpretability.
Our next paper looks at quality assurance for machine learning. Testing and monitoring are vital for assessing the production readiness of an ML system and minimizing technical debt. But how much testing and monitoring is enough? The authors in this paper present an ML test score rubric based on a set of actionable tests to help quantify these issues. So for each test, you get 1 point for executing the test manually and documenting it. If you automate the test, even better, you get 2 points. So your final score is now the minimum of the scores aggregated for each of the following 4 sections: features, model building, infrastructure, and monitoring. Basically, your system is as strong as its weakest component. Let's discuss a few different kinds of tests that can be performed. For example, of a test during the model development phase, you might want to test the relationship between offline proxy metrics and their actual impact metrics and make sure that there's a positive correlation. Say you just built a ranking model to rank products on a search page. Does the area under the ROC curve or NDCG, which are offline metrics, actually correlate with click through and conversion rates from A B tests? Next, let's look at a test from the features and dataset point of view. So you might want to test that the distributions of each feature over time match your expectations. Say a feature in your model is number of times an iPhone 10 was purchased today. A simple technique would be to keep track of the moving average of this quantity over time and then raise alerts if this metric on any given day changes by more than, say, 2 standard deviations. You also want to have tests on the infrastructure side of things. You might want to test how quickly and safely a model can be rolled back to previous version. Let's suppose you find a bug in your fancy neural network ranking model and the search results suddenly are not as expected. Now you need to switch your ranking model to a previous working version. Being able to quickly revert to a previous known good state is crucial for ML models. Finally, you need tests for monitoring. You want to test that your training and serving features computed the same values. Oftentimes, what happens is the data scientist will train models offline using data from a data warehouse using Pig or Hive or Spark. But at serving time, the data comes from a real time system. In such cases, it's essential to test that the training and testing values from both sources are exactly the same. If they're not, then alerts should be raised. Please see the paper for many more times.
There are various technical tests that we saw in the original paper that can be solved by model interpretability. Before delving into those tests, let's look at what does it mean by the models to be interpretable. Depending on the context, interpretability may refer to the faith in the model to generalize and perform well on the unseen data, or it can refer to understanding features, parameters, or training algorithms, and even tracing back why a particular result is obtained. Let us now go through what are desired outcomes of interpretable models one by one and how they can be applied to the technical debts mentioned in the original paper. Trust in a model can be defined either objectively through accuracy and validation sets or subjectively through understandability of the model. A person might feel at ease with a well understood models in situations such as forecasting crime rates. Thus, trustable models are easier to understand and integrate in large machine learning pipelines, and hence they make collaborations between engineers and researchers easier. Machine learning models are often used to uncover correlations occurring in the natural world. For example, a regression model might reveal a strong association between smoking and lung cancer. These correlations can then be verified in control settings and hence mitigate the technical debt of non causal correlations. Bayesian neural networks are interpretable and thus better able to provide clues about the causal relationships between signals and states. The next desired outcome of an interpretable model is transferability. It signifies how well the model can transfer learned skill to an unfamiliar environment. The model itself can change the environment and hence invalidate itself, a technical debt called feedback loop, or the model might be deployed in an adversarial settings. Deploying machine learning in production might involve convincing stakeholders like product managers, politicians, and executives who might not be familiar with machine learning. This calls for a strong need to produce informative models, thereby mitigating technical debt of communication barriers. We now turn to consider the techniques and model properties to enable interpretations. These broadly fall into two categories. The first relates to transparency, that is, how does the model work? The second consists of post hoc explanations, that is, what else can the model tell me? The first aspect of transparency is simulatability, which refers to a human being able to simulate the output. From this perspective, Long lists and deep decision trees are less transparent than, say, a compact neural network. From the perspective of algorithmic transparency, we can see the shape of error surface of linear models and hence comment on the convergence even on the unseen data. But deep learning models lack such transparency. While post hoc interpretations do not elucidate on how a model works, they may confer useful information for the end users of machine learning. For instance, a learning system can comprise of two models, one model to generate the predictions and another to generate the text explanation. In a neural network, we might not be able to interpret the full mapping learned, but we can explain the local outcomes by visualizing map of cells in an LSTM for different inputs. Other techniques include explaining through examples and visualizations. The next work, called Counterfactual Reasoning and Learning Systems, deals with mitigating the technical debt of non causal correlation. Imagine a model that learns correlation between two features. But what if this correlation is just coincidental and does not imply causation? If the world suddenly stops making these features co occur, the prediction behavior of the model would change significantly. Another technical debt of ML systems is modeling complex interactions. Consider an ad placement system in a search engine. The placement depends on the bids of advertisers and on score computed by ML systems. In these systems, there is a web of different features being dependent on each other, like clicks of users, advertiser payments, future bids, user experience, and so on. Other causation issue in ML systems is the presence and identification of confounding variables. In this example, a treatment A and B were applied to patients having kidney stone. If we look at the overall rates, treatment B is better. But if we further divide our treatment and control groups into patients with small stones and large stones, we see a different story with A doing better. We can notice that treatment B was more frequently prescribed to patients suffering from small kidney stones, that is, a less serious condition. Did treatment B achieve a high success rate because of its intrinsic qualities or because it was applied to less severe cases? Hence, here, stone size is the confounding variable. To systematically think about complex causal systems, we create causal graphs signifying relationships between different variables. We use the principle that causes precede the effect, and hence the graph should always be acyclic. This graph can be easily converted to Bayesian belief networks and can be modeled using Markov factorization. Here we look at the example of computational advertising. We now tackle the problem of reasoning about the effect of proposed change in a learning system due to changes in the external world. We talked about this technical debt in the original paper. The designers of the ad placement model would often face the question of testing whether a proposed modification results in improvement of performance. The simplest way to answer the question is to try the modification by randomly splitting the user into treatment and control groups. But this is very expensive to completely implement the modifications. And in case of multiple stakeholders like users and advertisers, it is impossible to control all of them. Thus, we would want to leverage the causal inference in some way to predict the consequences of modifying a system. Counterfactual reasoning is one such method that gives answers to hypothetical questions without actually implementing the modifications. The main idea of counterfactuals is simply answering questions like what would have happened if an intervention was performed? One of the techniques is to simulate the effect of modifications on the past data while taking into account the confounding variables. Here, since Bayesian models and Markov factorizations are being used, the intervention refers to changing one of the Markov factors p to p star and calculate the new expectation or the counterfactual expectation of any quantity of interest which here is L omega. Y is the original expected yield on P, while Y star is the expected yield after applying the counterfactual. Y star can be approximated through the statistical concept called importance sampling. Notice that we do not know the distribution P star, but we know the distribution P. We approximate Y star by sampling from P by reweighting each sample by the weight given by P star upon P. This ratio is just the factors appearing in P star but not in P divided by the factors appearing in P but not in P star. For comprehensive analysis of counterfactuals, one should look at the cited paper. Now, Mihir will talk about human challenges in machine learning.
Alright, so far we've been looking at the technical challenges that are faced by modern machine learning deployments and how they can be mitigated. But as with projects in any domain, there's a lot more going on than just putting quality code into production. In light of this, the next paper outlines human challenges posed by data science projects. These projects have a multitude of humans playing very different, even opposing roles. So the key players include the product manager, who wants to embed some kind of smart experience for the users or drive the decisions on what should be built next. You have the software engineers who want to build or utilize ML software tools that can be well outside of their comfort zone. You have the legal and risk departments, which may influence design choices and data access. You have the operations teams, which are requested to maintain ML systems over time. And then finally, you have the ML practitioners. These guys should be able to communicate with all these above stakeholders to successfully build a reliable system. So ML-based projects can be divided into three phases: ideation, execution, followed by operation. Each phase comes with its own set of challenges. Let's take a running example of an e-commerce company that wants to build a chatbot to sell its products. In the ideation phase, you have your product managers and designers, and they want to explore the potential impact of an ML system and make a decision as to whether the idea even deserves funding and resources, such as engineers or compute resources. There can be a lot of unknowns here, such as will it really drive more sales? Is a chatbot really required? Do I have sufficient data to build a chatbot? Then there can also be a lot of challenges related to privacy. A decision needs to be made whether to log the geolocation or the lat long of our users to personalize their experience. Then you have the execution phase. In this phase, generally a data scientist or a group of data scientists will do some exploratory data analysis and come up with a prototype model. And then you'll have some kind of offline qualitative validation, something like precision or recall. For our chatbot example, in this stage, many more challenges can arise. For instance, the product team may find it easier to use off-the-shelf APIs, like the Cortana Skills Kit provided by Microsoft, to build the bot, since this is a faster way to build and roll out the system. The data scientist might argue, you know what, let's propose an in-house solution which is optimized for our specific task. How do we resolve these conflicts? Also, sometimes a data scientist proposes a solution that performs really well in the lab, but turns out it's really hard to scale. The engineering team in such a case may instead prefer a simpler, possibly less accurate model that is instead easier to scale and maintain. If all goes well, then a development team needs to polish and productionize the prototype, while the data engineering team needs to secure the stability and availability of the required data sources. Even after deploying, there are many challenges that can come up. Let's say the chatbot didn't boost the sales as expected. The product team might come in and say, you know what, this was a bad idea. We want to remove the chatbot since it's really hurting the business. But the data scientist could argue that more time is needed for the results to reach statistical significance. So this was just an overview of the human challenges that are faced by a modern ML project. It's good to keep these in mind as any company begins work on a new machine learning related project.
Here's a summary of the work on technical debt we have covered in this video presentation. The original paper by Scully et al. Gives an overview of the challenges in ML deployment, which they call technical debts, and it also suggests some anecdotal heuristics to avoid these. The paper What's Your ML Test Score by Breck et al., also from Google Research, takes this work a step further by quantifying production level quality assurance techniques for ML applications. The technique suggested actually overcome several of the challenges outlined in the original paper. An ML model is acceptable only if stakeholders can trust it. Interpretable models account for easier communication and also are easier to integrate into production level pipelines. This aspect of interpretability is covered by Lipton et al. In the paper, The Mythos of Model Interpretability. The original paper also looks at assumptions such as feature correlation failing and how to deal with those. The paper counterfactual reasoning and learning systems, the example of computational advertising, looks at ways to predict the outcome of proposed modifications without actually implementing them. Finally, a new aspect which none of the above papers look at is the aspect of human and organizational challenges in productionizing machine learning algorithms. This is looked at in the paper Deploying Machine Learning Solutions in a Software Company. Thank you. We hope you enjoyed this presentation.